Oh, I hate to break this. I hate that second part was so small. Let us hope that this third part completes. But if I'm looking at some point on axis, then I've got, okay, that electric field, some distance d away, and then the electric field due to the negative charge will also be the same distance away but in a different direction. Now, one thing that we should be able to see here is that if I break these into x and y components, or parallel and perpendicular components, let's say, that the two components in this bisecting plane cancel each other out. So, what I get is if I call this angle theta, is that the angle they're picking as theta just for, I don't seem to do it. If I call this angle theta, then, okay, that angle's theta, this angle's theta, so it's the opposite side, so the net electric field is 2, because I'm getting a contribution for each, kq over the distance squared times the sine of theta, and kq times r squared plus s over 2 squared, the distance, times the sine of theta, which is the opposite, s over 2, times the hypotenuse, the square root of r squared, plus s over 2 squared, and that will break down. Again, the math is done there, but the electric field in that case will be given by, oops, sorry, there's a 2 that arrives in that first case, and in this case there is not, simply kp over r cubed. Which means that here at this point the electric field is, oh, and that's in the negative direction, so the electric field strength goes from k times p, which is the charge times the distance between them, divided by r cubed here. And if I were to look at that same distance r on axis, the value would be twice as high. So the value any other place would have to be between those two somewhere.